Okay, so it looks like we're recording. So last time we were talking about Chapter 3 stuff. We finished Section 3.2. Of course, we did 3.1 quite a while ago. So moving along to 3.3. So we're going to introduce a new kind of... Oh, I didn't turn the screen on. We're going to introduce a new kind of mathematical object called a vector field. Here it is, a vector field. What it is most fundamentally is a function, specifically a function whose domain and target are both not only Rn, but the same Rn. Right, so this is important. Rn to Rn. Same, has to be the same one. What's so great about these functions anyway, and why would we want to view them the way we're going to be viewing them with drawing pictures? It's two reasons. For one thing, it's going to turn out that these arise very naturally mathematically. So that's one, right? But the other is they also end up being a fantastic model for a lot of real-world stuff I'll pause on exactly what those real-world applications are. But this is the perfect tool to mathematically model a lot of real-world phenomena. So here's the big idea. The way we represent a vector field, a.k.a. one of these kinds of functions, geometrically, is whatever the input from the domain is, we view that as being a point. So here I have a point in R2, over here a point in R3. So we view the input as being a point. We view the output then as being a vector, not a point. We view the output as being a vector, and we represent that output vector with an arrow with its tail at the point that is the input point that gave rise to that output. Okay, so the point where it's defined is what the input is. The output, by the way, is called the field vector. So that arrow there represents the field vector at that given point x. Okay, so now right off the bat, it probably even occurs to you, just by looking at this picture, one of the applications that this is going to be the perfect tool for, right? Doesn't this kind of look like a fluid flow of some sort? Right, and so that's exactly right. One of our big applications is going to be that these are the tool for representing fluid flows. And there's more. Okay, but first let's get a little bit more accustomed to dealing with what these things look like and how to understand them. I do want to emphasize these pictures that we're drawing here, not a graph. Very important. These are not graphs. They just aren't, right? I mean, look at the definition of a graph. That's not what this is. It's not a graph. It's not a level set. It's not an image. What is it then? Well, it's yet a different way to represent a function, a multivariable vector-valued function, with a picture. So anything that you thought you recalled about how, wait a second, calculus, the way we interpret derivatives, for example, of multivariable functions, well, yeah, it's like it's a slope or it's a tangent line or it's an orthogonal vector or any of these things that you recall that in other contexts make sense, not in this context. And we're actually going to have to wait a while, by the way, to see what could reasonably be called the calculus of vector fields, right? What kinds of derivatives make what kinds of geometric sense for these pictures? That's going to take a while to develop. Okay. All right. So here we go. First, let's try to understand this vector field right here. Notice that for every input point, for every x comma y, no matter what the input point is, notice that your field vector is always the exact same 2 comma 1. It's always the same vector. So what we have is a bunch of arrows here that are all representing the same vector. This is called a constant vector field. So, again, this kind of throws a lot of people. A lot of people think, well, isn't it, if it's a constant, isn't it supposed to be like horizontal or something? That's in a graph, right? So we have a completely different kind of a picture that we're drawing here. It's not a graph. All that intuition that you had for graphs does not apply here. So this, for example, It's an example of a constant vector field. Okay. All right, next one. Now this next one is not a constant. Notice that here for every point x, okay, well the field vector, here let me use this color. The field vector, golly, it looks like, oh that's too similar, isn't it? That purple and that blue, a little too similar. Let me pick, we'll try green. Yeah, there we go. This field vector kind of looks the same as the input point. But you have to keep in mind, the input point is being viewed as a point. The output has to be, in this picture that we're drawing, has to be viewed as a vector. Right? So when I say they're the same, I mean algebraically they're the same. So in particular, though, what is the vector? Well, the point corresponds to this position vector for that point. That is what it is. That's the same as the output. The field vector is the same as the position vector for the point. And the way we draw that, of course, tail at the point in question is like that. So this input point, thought of as a vector, is the same as the output vector. Everybody on board? Okay, and that noted, that gives rise to a bunch of points and corresponding field vectors that look like that. And all together, I leave it to you to think through, more sort of like, put in more points and think about more resulting field vectors, and it gives you something that looks like that. And now again, thinking about things in terms of fluids, it's like there's a fluid where there's a fluid flow where the fluid is emanating out from the origin or something. Okay. All right. Okay, here's another one. Let's look at this vector field right here. And let's see here. I can zoom to see better. There we go. As usual, for any given point, here's a point. Don't forget that the point can be understood by its position vector. Here's our field vector. Now, not the same, but you do see the x and the y and the x, and they clearly have something to do with each other. You're going to notice a couple of things pretty quickly. One is these two vectors have the same magnitude. How about that? Right? That's an eyebrow raiser. It means something. Another thing you're going to notice pretty quickly, just for this particular one, the dot product is 0. How about that? So this field vector has the same magnitude as the position vector and is perpendicular to it, which immediately reduces it down to two possibilities. It's either that vector or this vector. Those are the only vectors that have the same magnitude and are perpendicular to the position vector. So which one is it? Well, I'm going to leave this linear algebra as an exercise for y'all, but this transformation can be viewed as a function, forgetting about vector fields, just viewed as two-dimensional vector in, two-dimensional vector out. It's a linear transformation, and specifically it's a quarter turn counterclockwise, and that means that it's this vector right here. And again, sort of thinking that through at a bunch of other points pretty quickly gives rise to the idea that altogether this represents this picture, and that's what I like to call the stirred pot. If you're looking down on a pot or a pan of water and you stir it counterclockwise, you get something that looks kind of like this. Is that cool? Everybody happy? So notice the intuition for what does the picture look like in relation to what is the formula. It's not familiar. It's not just like other stuff we've seen, right? So there's a whole new intuition that you have to develop. All right. Okay, let's see if I can. There we go. Okay, so moving along. Here's a physical example. This vector field right here. A little bit weird formula. I'm going to, first thing, rewrite it. Observe that that's exactly the same as this right here. And what's nice about this phrasing on the right, even though it's a little clunkier, a little bulkier, notice something really nice happens, and that is we see that there is a unit vector telling us the direction that these field vectors point, and there is a magnitude, a scalar that's telling us the magnitude, therefore, because it's being multiplied by a unit vector. Right? So this is what's called a radial inverse square vector field. Radial because x divided by the magnitude of x is always a unit vector pointing outward. Always outward. That's the term radial. And inverse square because the magnitude goes as the inverse square of the distance from the origin. All right, does that make sense to everybody? Everybody with me? Radial inverse square. And this is worth noting because there's a lot of vector fields that look exactly like this. Gravitational fields, for example. Exactly this, right? Gravity always pulls you towards the center of the Earth, so it's always radial, and it has an inverse square magnitude from the center of the Earth. Right? Anybody happy? Okay. Now, of course, a lot of people get weirded out by this and think, wait a second, but this is an outward normal, and gravity is inward. So what's up with that? And the resolution there is that this constant can just be negative, such as how I have it drawn here. And so to make this a gravitational field, you need C to be negative, and that's no problem. Now, also, this could be an electric field. As it turns out, electric fields and gravitational fields, the formula, for what's created by a single point, mass or charge, exactly the same. And that's a really useful, really important fact that's we're going to make a lot of reference to later on in Chapter 7. So that's just a little foreshadowing. Okay, so this is the other big application that I was mentioning that, again, why do we care about vector fields? And, they arise mathematically in natural ways. We're about to see one in a second. But they also are good physical tools for modeling real stuff. And I've already persuaded you, I hope, that fluid flows, perfect thing to be modeled by vector fields. And now here's the other big target for which this is the perfect mathematical model. Force fields, gravitational fields, electric fields, stuff like that. Magnetic fields as well. Okay. All right. So here's one of the natural sort of mathematical appearances of vector fields. Y'all recall that if we have a function, we can talk about the gradient. No big, right? If you have a real valued function, for example, that right there, right? Then you can just compute the gradient, no big deal. The gradient in that case is this, and lo and behold, and we didn't think of it this way when we first started talking about gradients, but check it out, the gradient is a vector field. Right? For any given point in the domain A comma B, here's the corresponding field vector for the gradient vector field. So it's just, there it is. I mean, we already know gradients are intrinsically interesting things. What kind of an object is a gradient? It's a vector field. So vector fields arise mathematically in very natural ways. Exhibit A. Okay. All right. So now just a quick reminder, we already knew that gradients always point uphill, and notice this vector field this vector field down here, if I were to think about that formula in the xy plane, right? Notice that the field vector is always twice the position vector, kind of like that other vector field that we saw on the previous page, except 2 times, right? And so that gives us, again, these kind of outward pointing field vectors like that. And note, sure enough, compared to the graph of this function, right? Compared to the graph, the gradient is always pointing uphill on the graph. We previously knew this We knew this one point at a time, as it were. What we see now is that it's doing so all points simultaneously. This is just a reinterpretation. This isn't a new result. This is a new point of view on an old result. Okay. All right, now let's talk terminology. There's an awkwardness here. I think if you have a function of which you take the gradient to thus get a vector field, there's pretty natural language that I think we should use here. The thing that you get when you produce the gradient, how about we call it the gradient? I mean, couldn't be easier, couldn't be more natural, the obvious choice. Quick reminder, when you have a single variable function and you take the derivative, the result is called the derivative, right? So, I mean, of course, perfectly obvious, what could be more natural? If you start, though, with the derivative and you ask, what was the thing whose derivative gave me that? We have terminology for that, too. It's called an antiderivative. So, likewise, given a vector field that is a gradient of something, what do you think we should call that something? I think we should call it the antigradient. Perfectly natural, perfectly analogous to the single variable antiderivative. Makes perfect sense to me. Okay, so that's the term I want to push. That's the term y'all are going to hear me say. Now, that said, here's a little reality of physics. It turns out that if you have a function giving you potential energy, this is just a quick physics aside. If you have potential energy and you take the gradient of it, you don't get the force. But if you take the negative of the potential energy and take the gradient, then as it turns out, what you get as a result is the force. And so, think about gravity, for example. Potential energy is higher at higher altitudes. It's lower at lower altitudes. If you were to take the gradient always points in the direction the function is increasing. The gradient of potential energy points up, because that's the direction potential energy is increasing. But which way does gravity pull you? Down. Right? So that's where this minus sign comes from. That's just the way potential energy got defined. It makes sense. It's necessary. So the reality, though, is that it's tempting to say that potential energy is the antigradient, but it's not quite, is it? It's off by a minus sign. Now, that said, it is still actually very popular, and I think really unfortunate, but very popular to refer to the antigradient as being the potential function, motivated by this little reality of how potential energy works. Now, it's not. The antigradient is not potential. It's the negative of the potential. I think that makes this extremely confusing. Anyway, that's what they do. So heads up, be aware, outside of this class, and maybe even a little bit in this class, you're going to hear me say the word potential function sometimes. It's just an alternative terminology. I will mostly be talking about antigradient. And then when you get outside of this class, again, you're going to hear the word potential function, by which they mean, very importantly, the negative of the potential energy. And I'm sorry. That's it's what it is. It's not my fault. All right, how are we doing? Does everybody see what I'm talking about here? Okay, moving along. Okay, so we've already seen some examples of this kind of hand waving, quickly. But vector fields can represent fluid flows, right? And so now we live in a three-dimensional world, and we tend to think three-dimensionally, and so there are some obvious three-dimensional fluids, the way air flows in this room or in the atmosphere, the way water flows in the ocean, the way pollution moves through a lake or a river or whatever. This is all three-dimensional, and likewise, how's the ozone moving around in the atmosphere, stuff like that. Okay, so plenty of those examples. What about two-dimensional? Well, we don't live in a two-dimensional universe, but we do live on a two-dimensional planet surface. right? And so two-dimensional fluid flow really makes sense too, and is actually pretty relatable. So the way water flows on the surface after it rains, right? Pretty natural to view that as a two-dimensional fluid. Technically, it's three-dimensional because it's about that thick, right? But I mean, really, we think of it as two-dimensional. And I like to throw in there just for fun that I think animal migrations are actually a pretty natural thing to view as being a fluid moving in two dimensions. And before you object that, hey, wait a minute, animals aren't fluids, they kind of are in a way, depending, right? So, for example, I mean, a lot of people would point out, hey, water isn't made up of individual things, right? A herd of wildebeests is a bunch of individual wildebeests. Well, at a molecular level, water is a bunch of discrete individual things, right? So animals are just a slightly coarser fluid in a weird way. So anyway, something to think about as wildebeests, travel across the savanna. Kind of a fluid flow. Okay. All right, now this next example has a calculation in it. We'll get to the calculation in a minute. First, I want to talk about, roughly speaking, what is the calculation about. The idea here is we're going to start with a vector field representing the velocity of the fluid. For whatever it's worth, I think this is a pretty natural first step, first attempt, right? First point of view at how we would represent a fluid with a vector field, right? So, for example, the air is moving in this room. I think I hear the air is on over there. I'm talking and blowing air, and other people are talking or whatever, breathing, right? There's air moving around in this room. And at any given point, the air at that point is moving with a velocity. So at that point, if we associate what is the corresponding velocity at that point, there you go, vector field, pretty natural. Right? Okay. Here's a natural question that you can ask that sounds very similar but isn't. And that is, what is the flow rate? So flow rate says I have maybe I have a screen of some sort here in my hand, right? Or maybe we're talking about out in the ocean and there's water flowing around with various velocity, whatever, and fisherman's got a net, right, that's sitting there. And as the water flows through the net, that's how they catch fish, something like that. So the point is, given an area, given a little piece of area sitting in space, and given that the fluid is flowing with a velocity, you could reasonably want to talk about how much volume per unit time of fluid is passing through that area. That make sense? So it's very important not to conflate these two things. These two things are different. Velocity is in feet per second, or meters per second, or whatever. Flow rate is volume, not distance. So cubic meters per second, not meters per second. So they're very, very different things. And given a vector field representing the velocity of the flow, reasonable question, how would I compute the flow rate through a given surface? Okay, so here's the calculation. There's a bunch of details here that just have to get done. Keep in mind the surface is inside of a plane, and that plane has a normal vector. Okay. Let's see here. We can talk about the fluid flow. Again, we have the vector field representing the velocity, and in some little small amount of time, I can talk about how much actual distance did the fluid actually flow in our little bitty amount of time, delta t. Right? And given that I have this area down here, if I want to know the grand total amount of fluid that has flowed through that surface in that amount of time, grand total, it's going to be this parallelepiped here. And so when we want to talk about volume per unit time, I really just need to compute the volume of that parallelepiped. That's it. I compute the volume of that parallelepiped, divide by delta T. That's the flow rate. Everybody happy with that so far? Okay, so now let's compute that volume. This is just a bunch of details at this point. Let's see here. We've got our basic formula here. Let me go into, well, you know what? I'll do it like this. I've got my displacement vector. I've got my area. Right? I can talk about the height of the resulting parallelepiped. Height times area gives me volume. Okay, wait a second. What is the height? Well, the height I observe from the picture is, oh, whoops, wrong color. The height, there we go, is the normal component of the displacement. That's just right there in the geometry of the picture. Right. Handy, I have a formula for how to compute components. And let's see here. We have also, what is this displacement vector? The displacement vector is velocity times time. Velocity, of course, being the vector field. So there you go. The displacement vector is vector field F times delta T. So altogether then, let's see here, cleaning up the mess. What we have is color choices. Volume divided by delta T gives me the result. So the flow rate dV dt is just this right here, namely F dot N times area. And this is a really important quantity. This is going to be the answer to a lot of questions. It's going to be a tool that allows us to do a lot of powerful things. This is deserving of a name and a notation. We're going to see most of that later. But here it is. It's called flux. It's just a word. It's a scary sounding word, but it's just a word. Flux, it represents the flow rate of fluid through a surface for the given vector field. And we use capital Greek letter phi to represent that. Let me pause on this. Make sure everybody's okay. Is everybody all right? All right, now one thing I want to point out, this could be negative. After all, you look at this formula here, there's a dot product in this formula for flux. The dot product you see right there, what if that dot product's negative? What does that mean geometrically? Right? So now, okay, here's the little catch. When I started this calculation, I said, well, we've got some normal vector that's perpendicular to the surface. Well, wait a minute, there's two of them. There's two unit normal vectors perpendicular to the surface. Which one do I pick? Which one's the right one? Which one's the wrong one? And you can see, depending on which one you pick, like as I have in this picture here, if I had picked this downward pointing normal vector, F dot N would be negative. What would that mean? Right? So the good news is there's not really a right answer on this. There's just a natural interpretation of your choice. When you pick this as your normal vector, that's just your indication of what you're calling the positive direction through the surface. Right? And here, with the vector field drawn as it is, there is fluid flowing through the surface in what we're calling the positive direction. Okay. On the other hand, had we decided, for whatever reason, whatever the context. I don't know. Every context is different. If it would have been natural to view this as the positive direction through the surface, right? And let me just remind you, as an example, basketball, ball has to go downward through the hoop, right? The direction that something passes through matters in some context. So if, for whatever reason, downward were the positive direction, what I want to consider the positive direction. Okay, well, if that's the positive direction, well, my fluid's going this way. The fluid is going opposite of the positive direction. I should get a negative answer. I would want to get a negative answer in this case, because if that's the positive direction, then this is the negative direction, and this fluid is, in fact, going in that negative direction. So, the flux keeps track for you of whether the fluid flow is in the positive direction or the negative direction, and it's your job to pick, by virtue of which normal vector you pick. This, by the way, is called an orientation vector. You need to think carefully about which one you would like in your context, given whatever it is that you're interested in here. Which one do you want to view as being positive? All right, let me pause on that for a second. How we doing? Okay. All right. Okay, now, I think this is a really good calculation right here. This picture, this resulting algebra, getting down to this result right there. Let me just remind you real quick, what we've shown is that if, and our very first assumption, the vector field represents the velocity of the fluid, then the result was that the flux, I kind of missed there. The flux represents our flow rate. Vector field being velocity, the flux gives us volume per unit time. All right, now what I want to leave as an exercise for y'all, you're going to really, really closely stick to this calculation that I've done here. Right? It's going to be almost exactly the same, just a little bit different. It's a healthy exercise to think about how to tweak it. If instead, if your vector field represented not velocity, but density times velocity, then this expression down here, this, flux, the same formula here, same exact formula, F dot N times area, no longer represents volume per unit time. Now it will represent mass per unit time instead of volume per unit time. So it's a nice little exercise. It's a good check to make sure that you're really following what's going on here, and it's also a good way to sort of prevent you from you don't want to go intuitively all in with just one point of view on how vector fields represent fluids. Sometimes what you want to know, depending on the situation, sometimes when you talk about flux, what you really want is volume per unit time. That's what you need sometimes. On the other hand, sometimes, pretty believably, I think, sometimes what you need is mass per unit time. You don't care about volume. I need to know mass per unit time. In which case, you can make that happen. You can make flux represent mass per unit time. You do so just by having the vector field be density times volume. Density times velocity. Sorry. Okay. Nice exercise. Again, stick very closely to what I did here. Minor tweaks only. As usual, these little, optional suggested exercises that I propose in class. If you get stuck, come to office hours. I'll be very happy to talk you through it, answer questions, whatever. Feel free. Okay. All right. Now this page, I am going to be quick about this page. This is supplemental. I just want to address certain realities I think are not only interesting, but essential and useful in some contexts. So I want to recognize that there are different kinds of fluids. And, we talked about water. Water is a natural thing to view as a fluid. It's like the stereotypical fluid, right? Air, it's a fluid, pretty believable. I'd like to propose that light could reasonably be thought of as a fluid. Right? And so in the sense that, like, if I had a light bulb right here, right, light bulb right there, and I flip it on, what happens? Well, the photons start flowing outwards, right, in all different directions. And so it is a bunch of particles, to be fair, but it is nevertheless a bunch of particles that are all kind of moving along with each other. It's kind of a fluid in a way. But it is a different kind of a fluid. So here's what photon fluids can do that water can't. If I have a light bulb right there at the orange spot, of course that starts shooting out light every which way. And in fact, then there will be a little bit of a light flow that way at this point, coming from that light bulb. But as is often the case, we might have more than one light bulb. What if, oh, that's too similar. Let me go with, I'll go with blue. What if we have another light bulb right there where I have the blue spot? That's going to be shooting out light every which way, including, at this point, the flow would be kind of like that. So now let's talk about how we would represent this very plausible real-world scenario. You can have two light bulbs in the same room, right? We have more than two. How would I describe the flow of the fluid of photons at this point? We've got a nasty little problem, because at that point, lights go in multiple directions, not just one direction. What vector should I choose to represent this flow of photons? And I remind you, this is a new thing, right? Because air, you can't have air at a single point moving two different directions. At a given point, sufficiently small little region, little piece of air, it's all kind of going pretty much the same way. Same with water. New problem that we're seeing only for photon flows. So how to deal with that, and there's a way to do this. You have to kind of abandon the idea that the vector field is going to represent velocity exactly, right? But remember, we already have this formula right here that says, suitably interpreted, you can view flux, this expression right here, as representing flow rate, this time mass per unit time, passing through a given surface. So here's what you can do. I might not be able to talk about velocity, but I can, for any surface, I can just empirically measure how much, quantity in whatever sense you prefer, quantity per unit time of photons are flowing through that surface. That's just empirical. I can just measure it. And there will be exactly one vector field that makes this equation work for all such surfaces. So rather than thinking of the velocity as a given and flow rate as something you determined from that, we're turning this equation around. We're taking the flow rate as what's given, in this case empirically, and we're defining the vector field from that. Okay, so I just wanted to point out that this is something that can be done. This is a quite a little bunny hole that we just cannot go down right now, especially since we're behind schedule. I'm sure you've noticed. Let me address that real quick. We're always behind schedule in my classes. I deliberately front load the schedule so that I will be constantly reminded that I am in a hurry. We have so much material we have to cover, and I have to make these tough choices that I hate having to make, but I have to do it. That's just the nature of the course. So we will catch up. It's fine. But with that in mind, this example that follows down here, this is highly supplemental. It's really not part of the standard definition of the course. And so as much as I think this is an awesome example and I really like it, we don't have time for this. So you are officially absolved of all responsibility for this example. As always, anyone who's curious, wants to, anyone who's intrigued by this, you want to come talk about it, come to my office hours. I would love to discuss this with you. Okay, but you're not responsible. Okay, moving along. So here is a related idea, something called a flow line. The scenario here is actually pretty believable. I think this is a very natural thing to want to do. So given a vector field, again, this to be interpreted as representing a fluid flow, in particular by the vector field telling us the velocity at any given point, let's just say. If that's the case, and if you were to have a particle, some little perfectly buoyant, I don't want to worry about gravity, stuff like that, but a perfectly buoyant particle that gets dropped into that fluid, that particle would follow the current, wouldn't it? That's pretty easy to see. You can go to a river, right, a creek or whatever, and just kind of take a dead leaf from the ground and just kind of toss it in there. It will follow exactly the path that the current tells it to follow, right? Wherever it is, whatever direction the water is going, that's the direction that leaf is going to go. Right? And so the resulting path that gets created is called a flow line. Now, it's a curve, not a line. That's just terminology. Sorry about that. It's a little awkward. Really, it ought to be called a flow path or a flow curve. But anyway, it's called a flow line. Okay, now how would we understand that path? How would we compute the flow line? And here's the big observation I'm going to zoom in on so I can, there we go, focus on this for just a minute. And I'm going to just kind of talk through the reasoning that leads to this little model. If you have a particle, and if you want to know what is the velocity of that particle, well, I mean, as we discussed, wherever that particle is, whatever the position of that particle is, the velocity is going to be whatever the velocity of the water is. Right? Whatever the water does, that's what the particle does. Right? Everybody good with that? Just kind of writing down what we've understood intuitively. And then keeping in mind, as previously discussed, the vector field is, of course, representing the velocity of the fluid, velocity of the water. And so all together, just having written this down carefully, we end up with what is called a system of differential equations. Right? So you can see it's a differential equation. Well, it's an equation because of the equal sign. It's a differential equation because there's a derivative in it. You can see that whatever my vector field is, that's going to tell me the formula for how to relate the derivative to the position. And you can write these things down, and again, you get a system of differential equations. Now, how do you solve a system of differential equations? That's a whole nother thing. And that is not something that we do in this course. That is something that y'all will see. Whichever of y'all are engineers are going to see that in Math219. Right? It's just it's a long conversation, but ultimately not that big a deal. Okay, so the solution is called a flow line. And now here is an exercise. Again, I think this is a healthy exercise for everybody to do. If you were to take this vector field, remember this is our stirred pot. Right? We looked at this example a little while ago. If you were to take that vector field, in other words, imagine the stirred pot, and then to that stirred pot, if you were to write down this differential equation, this system of differential equations, and if you were to solve that, which you don't know how to do yet, so don't try, right? But what you would find is that this right here is a solution. This will solve that differential equation, or said differently, that is a flow line for this vector field. And, oh yeah. Mm-hmm.
How can you check that it's a flow line?
Yeah, exactly. So the way you're going to check this is by just plugging in and confirming that the equation works. So you're going to take this formula for x, and you're going to take its derivative, like the left side says, right? And then you're going to take this same formula, and you're going to plug it in here, and you're going to apply this vector field to it, doing whatever this vector field says. And then the way you're going to confirm that this has worked is you're going to compute both of these things and confirm that they are in fact the same, and thus the equation worked. Does that make sense? Okay. So this is, like I say, I think a healthy exercise. It's not much algebra. There's hardly anything to it. Take that derivative, do this to that proposed solution, confirm, you get the same thing. Okay. All right. And by the way, this tracks intuitively as well, because remember, this is a stirred pot, and now without any math at all, just your intuition about stirred pots. If you drop a bay leaf into your stirred pot, it's going to go around in a circle, isn't it? And of course, that's a circle. Yeah? All right. Okay, moving along. Just a quick. I want to head off a bad idea that a lot of students have. A lot of students look at this discussion that we've been having about how vector fields represent fluids, could represent fluids, that is, and develop a certain amount of satisfaction with that, whatever that amount of satisfaction might be. And then they look back at the earlier examples where vector fields can represent forces. Totally different physical metaphor. Forces are not fluids. Fluids are not forces. Right? Totally different. And they have a certain amount of intuition for that as well. And in some cases, students will find that they like one better than the other. Right? And they make a subconscious decision, you know what, I'm sticking with fluids. I don't like this forces business. I like fluids. Or perhaps vice versa. Like, I don't know what the deal is with the fluid nonsense, but I get gravitational forces and electric field forces and stuff like that. And you can't. So very importantly, both, let's see, what happened to my, there it goes. Both forces and fluids, both of them are critical to future work in this course. There is going to be applications where you have to think about vector fields as representing forces. And there's going to be applications later in this course where you have to think of the vector field as representing fluids. So please don't pick one. Please make sure that you start to digest and develop intuition for both of these physical metaphors. Okay, 3.4. This is a weird topic to insert at this point in the course. I wish I could delay this to later in the course. But the book introduces it now, and the way everything else is put together, I really kind of can't delay this. So let me just go on record first as saying that there's some really unnatural things about what we're about to do here. I am going to have to introduce some ideas without context. Not only am I not going to prove what I'm about to claim, definitely not going to prove it, I'm not even going to be able to give you a reasonable motivation for it. And I really don't like that. That's, this idea that I speak and you take on faith, I don't think that's at all appropriate, right? That's not what we should be doing here. So anyway, I'm not a fan, but this is what we face. So here we go. First, I introduce a notation. Y'all, of course, recall the gradient. I'm going to point out you could redraw that like this, right? Just kind of think about the, this is arguably an abuse of notation, but you know what I mean when I write this down. This, function goes in and has all three of these differential operators applied to it. Exactly this, right? So, like I say, a little bit of an abuse. Very common, highly accepted, perfectly reasonable notation. And then the idea is, well, then that kind of means that this thing by itself, not applied to a function, but that thing by itself could be thought of as a kind of a thing. And it turns out, we're going to see this later, turns out this is really, really useful. Right? So we give this a name and a notation as well. This is called the del operator. Let me, again, head off the bad intuition. A lot of people like to call this the gradient operator. That is a mistake. That's really not good. We're going to be doing far more things with this than just gradient. So you cannot call this the gradient. This is not the gradient. The green is the gradient. When you apply it to a function in this specific way, that's the gradient. This is the del operator, which has many uses and applications. So heads up about this. This is something we'll be using going forward, and I believe we are out of time, so we'll call it a day here, and see y'all on Wednesday. Have a good one.